And we are live. Live. Are we live? I think so. Vale and Davide, nice to meet you again today. And today we have Davide presenting a paper on
Attention is all you need.
Attention is all you need. Love it. Let me check on Twitch if everything goes smoothly, and go ahead. Yeah, please go ahead.
May I share my screen?
Yeah.
Okay. So this is the paper presenting classifiers.
One second. Mi sa che non abbiamo l'audio. Look back. Oh, guys, I'm so sorry.
1 second.
Yes, that's good. Go ahead.
Okay.
Mi sa che non abbiamo l'audio.
Is it okay, the audio?
Yeah.
Okay. So this is one of the most famous papers in the last few years. Attention is all you need is a paper presenting the transformer architecture. So this architecture is the first time invented for sec-to-sec models, meaning models that use an inner representation to essentially translate a sequence of data to another. For example, in this specific article, they use transformers to simply translate a sentence from English to French, for example. So what was the previous SOTA model for this type of task? Obviously LSTM, because with LSTM you can create an inner representation of the sentence, and then you can translate that representation in another language. The problem of this kind of architecture was that if you know how LSTM works, they essentially have an hidden state, a memory, that they use to keep track of the previous words in the sentence. On the other end, transformers is able to see all the other words at each step. And obviously, this capability of transformers is able to decrease largely the inductive bias of the model. So, what is inductive bias? The inductive bias of the model is a sort of prior of that we impose on the model to help him to converge quickly, essentially. For example, convolutional neural networks are really biased. Why? Because they try to find correlation only in a local way. They see only to the pixels that are in the filter of the convolution. This is a bias, obviously, because you say that usually the pixel is usually correlated to the ones that are around him. And in the same way, in LSTM, the bias is that you essentially read the sentence in a specific order. And so you say that the word is more correlated to the one that are closer to it.
Okay. Question.
Yeah.
Valerio, did you get the point of the paper that was just made by Davide?
Yes, I'm trying to figure out the sense of this schema here.
Yeah. Yeah. So this is the architecture of transformers used in sec-to-sec task. In this case, they use an encoder, that is the left part of this image, and a decoder. Okay.
But is the transformer the concatenation of the encoder with the decoder, or is some block in this picture?
Transformers is essentially a concatenation of multiple self-attention layers that are the building blocks of transformers.
Are they the orange blocks here?
Sorry?
Yeah. In my question is, in this picture,
Mm-hmm.
which are the block or the blocks that made the transformer?
You could say that there is a transformer in the encoder, the left part, and there is another transformer in the decoder. Okay, but this is a seminal paper about transformers. This is not the final architecture that we are using right now for the current SOTA models in NLP. There have been significant modification in this architecture. Basically, the new language model that they are using right now, like BERT, like GPT-3, they are using just the encoder part of this architecture.
Okay, so for people that are not familiar with transformers, let's step back 1 second. You said the transformers are essentially a concatenation of self-attention blocks, is that correct?
Yeah, so I would like to explain more what is self-attention.
Yes, what is it, self-attention?
Self-attention is essentially a layer that we can see here. The inputs of the layer are these 3 different tensors, basically. The query, the key, and the value. Okay. So the mathematical interaction among these 3 elements is explained here. So you basically multiply the query matrix with the keys. You normalize with the sides of the vectors, the input vectors, and you apply a softmax.
And just for clarity, what is the value, what is the key, and what is the query?
It depends. For example, in this architecture, as I said, is an old version of transformers. Query and keys are for example, if you're translating from English to French, query and keys are the English words, and values are the French words. But in the new architectures like BERT, query, keys, and values are computed directly from the same input, that is the sentence, basically.
Okay, here we're talking about NLP. Actually, we're talking about a very specific problem, which is translation, right? But from what you're saying, this value, key, and query can be arbitrarily set depending on the problem.
They are usually the same thing. And the reason for that is that you want to compute the inner product between the words in your sentence. So here you can see that query and keys are multiplied by each other. Mm-hmm. And this is a way to compute the attention from between the two words, for example. So if you think at this attention as a simple neuron, how it is made? Is made with a weight multiplied with the input, the input vector. So here, for example, you can see you can read the value as your input vector, and this softmax as the weights. Okay.
Yes. So the value is the weight.
The value is the input itself of the layer.
Okay.
And the softmax is the weight. That are basically the importance of a word to another.
Okay.
And you can see the power here of this architecture, because you can compute the attention to between two words that are very distant from each other.
Okay, so let's make an example. Okay, and the example is arg
Yeah,
softmax.
for example, you can say, I take out the dog in the street.
Yeah.
I don't know, which is my dog, which is my which. Okay.
Yeah, I lost you. You said it.
I took out my dog in the street, which is called Rex. That which in LSTM would be highly correlated to street, but in the common sense, it's obvious that which refers to dog. Okay. So in a transformer architecture, that which will be highly correlated to dog, and their inner product will be Ike.
Okay. Valerio, any doubts?
I got how a single computation of attention works. So basically, we are going to replace traditional neurons with many attention computation, many modules that compute the attention.
Yeah, because as I said, transformers are sequential application of this self-attention layer. This N means that this self-attention layer is applied N times.
So basically, instead of now I'm thinking to a multi-layer perceptron, let's say. So instead of having I don't know, 3 layers and then the output, we of 3 fully connected layers and then the output layer, for example, we in this case we have 3 layers that are not fully connected, but that are self-attention.
Yeah.
Okay.
But you can use transformers only in sequential problems.
Yeah. It was just to make a parallelism with traditional neural networks.
Okay.
And by the way, we're not going to cover everything on this paper, obviously, and there's going to be a follow-up discussion, even maybe before Friday, because this is very interesting. I just would like to better understand what is the advantage, the practical advantage of a transformer versus, a traditional deep multi-layer architecture. And even, brownie points, if you can give us another example. And by the way, I'm taking notes on my iPad. So while you're talking, Davide, I'm translating, or I'm trying to translate what you're saying into a visual example.
Yeah.
So I repeat the question. The question is, what is the advantage, the practical advantage of a transformer architecture versus a traditional multi-layer deep architecture?
Yeah. I think that you can naively think that multi-layer perceptrons are the best models in the world, because if you think about how it works, a classical neural network, you compute the interaction between each input in the neuron. I mean, each
okay,
neuron of the next layer is linked to each neuron of the previous one, right?
Okay.
So this is traditional neural nets.
Is the traditional one. And so you could think that the best model is the model with the lower bias. But I think transformers is more powerful because, as you can see here in the attention, the weights are computed on the fly. They are not static. They're not static. You compute the interaction between the input features on the fly when you are in the inference phase.
Wonderful. So
I
computed on the
want-
fly. I have a question. Sorry.
Me too.
Okay.
Me too. Go
We
ahead,
have
go ahead.
2 minutes. So Valerio goes first, and then we wrap up this first part.
So, going very, very deeply in the architecture, it's like while the weights or a traditional model are fixed, here the weights change according to the input.
Yeah.
Okay.
I mean, these queries and keys, and even values are computed with weights because
Yeah.
after this attention layer, after each attention layer, there is a classical layer that compute the queries, the keys, and the values for the next layer. So
Okay.
the weights, it's a different way to use the weights.
Okay.
Okay, guys, thanks a lot. Again, the scope of this Twitch live is to keep these discussions short and punchy. I think the paper is just a pretext to think together about a problem or a technique that is of mutual interest. So what I suggest is that we wrap it up here, and maybe next week we'll start again where we left it today. And we are going to freeze this conversation on the advantages of transformers versus traditional deep learning architectures. Thank you very much.
Thank you, guys.
Thank you, Davide.